Hi all. Today's class we can discuss one convolutional decoding problem. So in this decoding problem we are using VITERBI algorithm. So first we can see the question. For a 312 convolutional code with g of 1 equal to 100, g of 2 equal to 101, g of 3 equal to 111, decode the received code word 111, 101, 101, 011, 100, 111, 011 using VITERBI algorithm. So we can see that we are using convolutional code for different coding purpose. In that we can see that this encoding of this convolutional code was done using code tree or trellis diagram or state diagram, etc. And the same using this same we can decode our convolutional code also. That means in this VITERBI algorithm we are using the principle of trellis diagram to decode this convolutional code. So we can see how we can decode this convolutional code using VITERBI algorithm. So in this VITERBI algorithm, the main thing is it consists of two steps. One is the metric value assign, and the second thing is the path, active path, identification of active path. So we can see how we can identify the active path, how we can represent the metric value of each node, etc. In this problem. So our problem consists of a 312 convolutional code. It can the g of 1, g of 2, g of 3 all are given. So we can first to decode our convolutional code, first we need the state representation as well as the state transition with respect to input, and the corresponding output also we need. So first we need to draw this encoder circuit. From that encoder circuit we can easily find out what is the state transition. So these things we needed for decoding this VITERBI algorithm, as well as one more decoding algorithm is the for this convolutional encode, and that decoding algorithm is called as sequential decoding. That also we need this encoder representation as well as state diagram. So instead of drawing this encoder, you can directly also find the state diagram transition or state table representation. Then we can easily find out this VITERBI algorithm or sequential algorithm. So first step, we need to draw the trellis, required number of stages of trellis diagram. So to draw this trellis diagram we need the state table, or we need the state diagram, or we need the encoder circuit. So here we can first draw this encoder circuit. From this encoder circuit we can easily find out the state transition table or state table. So we can see that first we need to obtain the state transition table or state table, or we can also draw this encoder diagram. From that encoder diagram we can easily find out the state transition. So to draw this encoder diagram we need the number of output, and we need the number of inputs required, flip-flop, number of flip-flops required, etc. So in that so to find out that we have g of 1, g of 2 and g of 3. In this g of 1, this first bit represent the input connection, second bit represent flip-flop 1 connection, and third bit is the flip-flop 2 connection. So this g of 1, g of 2, g of 3 represent v of 1, v of 2 and v of 3 respectively. That means output code 1, output code 2 and output code 3 respectively. And in this we can see that this v of 1, that is input 1 is depend on input only, and input 2 is depend on input as well as last flip-flop, and this the output 3 is depend on input as well as both flip-flops. So we can first draw this encoder diagram. So this is the encoder diagram. We need two memory elements. We have one input, so that the first v of 1 there is no need of any adder. We can directly, the input connection is directly taken as v of 1, v of 2 is input plus this f of 2 connection is v of 2, and v of 3 is input plus this f of 1 plus f of 2, and this addition is modulo to addition. So from this we can see the state transition table. So we have S0 as the present state. Initial state we are considered as S0, that is 0 0 state, that is S0 here. So S0 is 0 0, S1 is 0 1, S2 is 1 0, and S3 is 1 1. So now we are assigning meaning that our present state is 0 0. At that time another input 0 is coming, so we can write now our input is in 0, sorry, our present state is in 0 0. Now new input 0 is coming, so that 0 is moves to this f of 1, and already the previous content of f of 1 moves to f of 2. That's why we will get again 0 0 as the content, so that is S0. So this way we can find the state transition. This one we already did this for one example, so we have this question. So the same question we need to encode. We are encoded the same question using tree diagram, tree list diagram, etc. In that we already found what is the state transition table. So this is the state transition table for the same question. So in that we can see that when present state is S0, that is 0 0. When input is 0, then output is 0 0. Sorry, the next state is 0 0, output is 0 0. And when the present state is 0 0, input is 1. Then next state is 1 0, that time output is 1 1. So for 0 1, 0 input, present state is 0 1, next state is 0 0, then 0 1 1 as output. Then next is for input 1, 1 0 is the next state, 1 0 0 is the output. Similarly for 1 0, for 0 input, 0 1 next state, output 0 0 1. And for same present state 1 0, input 1, our next state 1 1, output 1 1 0, then double 1 is the present state, then input 0, then next state 0 1, output 0 1 0. Now the present state is 1 1 and input 1 is coming, so that the next state is 1 1 itself, and the output is 1 0 1. So this state table we need to draw this tree list diagram or chord tree. We need the state table representation. So this, in that question we didn't include this state table because we already did this for another question. So for drawing this, so from this we can write this state transition. So this is the thing we needed to draw this tree list diagram. So what is the present state, what is the next state for 0 and 1 input transition, and what are the outputs. So this represent output, and this represent next state. This is input and this is the present state. So these things we needed for drawing this tree list diagram. So next we can draw this tree list diagram. So using this information, first step we need to draw the tree list diagram. So now we can draw the tree list diagram. So this is the main structure of this tree list diagram. So first we can see that how many received code words are there. So here we have 111, 101, 101, 011, 100, 111, 011. That means 7 combinations are there. So we need 7, total of 8 state representation here. So we need 8 dots here. So that means the number of depth, this dot representation is called depth of tree list diagram. So the total number of depth required is we can represent it as capital K. That means constraint length plus message length. So that is capital K plus capital L. That is capital K is the constraint length and capital L is the message input length. So, or otherwise, if you have 7 received code bits, then we have 7 transition is needed for this state also. So this is one transition, this is another transition, this is another one, third transition, fourth transition, fifth transition, sixth transition, and this is the 7th transition. So total of 8 depths are there for this tree list diagram. So first you mark all the depth, and then you respective transition you can mark the received code word above that. So for this transition we have the code word 111, for this transition 101, this all are the received code words. So first you mark the received code word, and from that you find out how many transitions are there, how many nodes needed for this, and we can say that that is received code word plus 1 nodes are there for this tree list diagram. Then you can mark the present state, that is S0, S1, S2, S3. Then we can see that from S0, this is the initial 0 for 0, 0 condition, present state is 0, 0. When input is 0, that moves to S0, then output is 0, 0. When for one input, we can represent as S0 moves to S2, having output 111. So in this trellis diagram, we can see that input 0 is represented as dark lines and input 1 are represented using dashed lines. So we can mark that transition. So this is for 0 input and this is for 1 input. So for that 0 case, output is, we can see that output is 0, 0. So we can mark that. So 0, 0. Then for this 1 transition, when the input is 1, output is 111, that moves to S2. So this is our first step while decoding. While using VITERBI decoding, this is the first step. So we need to draw the trellis diagram. So next we can see that next we need to find the metric value. That is very, very important. So to find the metric value, we can compare this received code bits with the respective output. So that branch represents the output. So here this output is 0, 0, 0. So we can compare this bit position changes for this received code word and this encoded code word. So here we can see that 1 is changed as 0. So there is a 1 bit change. Here again 1 is changed as 0. Again 1 bit change. Here 1 is changed as 0. Again 1 bit change. So total of 3 bits changes for this received code word and encoded code word. So we can say that the metric value is 3. This node value is 3. Similarly, we need to find this branch metric value with this received code word. So here it is 111. Our metric branch value also 111. So the metric value is, there is no bit position change. So the metric value is 0. So this way we can mark the metric value. So this is called metric value. Next we can see how we can identify the active path. So for that we can, so now at this is j equal to 0 and this is j equal to 1. So at j equal to 1 condition, we have 2 branches. So from this 2 branches, we need to consider what is the case if input is 0 and input is 1. So first, when input is 0, that moves to S0 itself, having output 0, 0. Then input 1, it will move to S2, having output 111. Then from this S2, we can see that when input is 0, then that moves to S1, having output 0, 0, 1. This all the things are obtained from the state table. Then when input is 1, that moves to S2 moves to S3, having output 110. Next, now we have 4 branches at the output. So this 4 branches we need to compare with the second received code bit. So here 0, 0 is compared with 1, 0, 1. So we can see that 2 bit positions are there. So total metric value we can write as, we can write this metric value as 5. So here the metric value is 5. Then we can compare this received code bit with this 111. So we can see that 1 bit position change is there. So we can see that 3 plus this 1, that is total cumulative metric value we need to write here. So here it is 3 plus here 2. So 3 plus 2 is 5 here. Here it is 3. Now we have only 1 bit change. So the total of 4. And here we have 0, but now 110 and 101. So we have 2 bit position change. So this metric value is 2. So now we have 4 branches. Then we need to consider input 0 and input 1 for this 4 branches. So total of 8 branches will be there. So we can see that we can represent respective output also. For every node we need to consider input 1 and input 0. So this way we can find all the transition from the state table. We will get the transition. So now we need to find out the metric value. So now we can compare this 101 with 000. So again 2 bit positions are there. Then positions are changed there. So we have a total of, we can see that 7 is the metric value. So 5 here plus 2, 7. So next we need to find what is the metric value of this branch. So here it is 1. Then we need to find the metric change of this 101 with 011. So we can see that there should be 2 metric change. So total of 3 should be that branch. So now we have 2 branches. One have metric value of 7 and one have metric value of 3. In this node itself we have 2 branches. One have metric value of 7 and another one have metric value of 3. So we need to find the active path in this node. Up to this node, which is the active path. The active path is the path having lowest metric value. So from this we can see that the 3 is the lowest value. So we can avoid this metric value 7 path. So we can discard that path. So now onwards there is no path corresponding this 7. So now onwards we will calculate the total metric value of this node as 3. So for each branch we need to find the metric value. So while finding this node, we have 2 branches are there for this node, but the metric value is same for both branches. So we can't avoid one branch. We need to consider both branches here because they have equal metric value. So for next branch we have 6 and 2 is the metric value. So obviously we will avoid the metric value having 6. The path having metric value of 6 we will avoid. Next we have 6 and 2. Then again that 6 we cancel. So this way we can find the active path of each node. Next we need to continue this up to this last received bit. So this way we can find this metric value and the active path. So here we can see that now we have 0, 0, 0 here, 0, 1, 1 here. So we have 2 bit positions are changed. So the cumulative now we consider not 7, it is 3 plus 2, 5. So we avoided this 7. So this way we can calculate the metric value as well as we can find out the active path this point onwards. So we need to continue this process up to this point. So we can see that. So this is the complete structure of VITERBI decoding. So we will calculate this and avoid the path having highest metric value. So we will reach at this point at end point, and from this end point each path have 2 branches. In that one with highest metric value we avoided. So here we can see that this path 5 and this path 9 the metric value. So we avoided this path having 9 metric values. Here we have 8 and 5. So this path having 8 is the metric value we avoided. So here we have 8 and 8. So we can't avoid any path. So here we have 8 and 6. So the path having 8 we avoided. So this way we can complete this trellis structure. So now we can find out what is the received code word. We can decode the received code word as well as from this received code word we can decode the message. So for that now we have branches having metric value. 5 is here, 5 is here, 8 is here, 8 is here, and 6 is here. So from this we can select a path which have smallest metric value. So here we can compare this value. So we have 5 is the lowest value from this metric value. So we can select the branches having lowest metric value. So here we have 2 branches. So we need to consider this branch as well as this branch for finding the decoding the input. So now we have 2 branches with lowest metric value. If you have the metric values like 5 and 5, 8, 8, 5 and this is maybe 3, then you can consider that path having 3 metric values. So now we can consider only the path having lowest metric value. So here the metric value, lowest metric value is 5. So we can consider that path. So we have 2 paths, one is this and one is this. Then we can find out what is the decoded encoded messages in that, so that the path with the lowest error, that should be the decoded path. So first we can consider this. So first is 0 1 1, then that moves to here, then this 0 0 1, then this point we can we are moving to this path. So that is here we have two branches, one is this branch and another one is this branch. So first branch we can write it as 0 1 0, then that moves to 1 0 1, then 1 1 0, then 1 1 1. So if you are considering this path, we have 0 1 1, then 0 0 1, then 1 0 0, then moves to 0 0 1, then next is 1 0 0, then 0 1 1, 1 1 1. So that's the two branches available for this active path. And for this active path we have 0 1 0, then 1 1 0. This path we already avoided, so we can't consider that. So from this 0 1 0, 1 1 0, then we can move to 1 0 0. Then again here we have two branches, we need to consider that two branches. So now we have total of 4 branches. So we can write that 4 branches output from this direction to this direction, so from forward direction. So then we can compare this received code word with this obtained code word. Then the code word with least error we are taking as the decoded code word. So here we can see that 1 1 1, 1 0 1, 1 0 1, 0 1 1, 1 0 0, 1 1 0 1 1 is the received code word. So we can check each position. So here 1 1 is 1 1 itself. So we have correct 1 bit combinations are there. Then this is 1 0 1, but here it is 0 0 1. It's not correct. Then 1 0 1, here it is 1 0 0. It's not correct. Here it is 0 0 1, here it is 0 1 1, it's not correct. Then 1 0 0, here also 1 0 0, it's correct. Then here it is 1 1 1, but here it is 0 0 1, it's not correct. Here it is 0 1 1, here it is 0 1. So we have 3 combinations are correct here. Next we can see that 1, 2, 3, 4 combinations are correct. In this we can see 1, 2, 2 combinations only correct. Then here it is 1 2 3, 3 combinations only correct. So from this we can see that the maximum least error is this 4 corrections. We have 4 combinations are correct here, so that have least error. So we will decode that as decoded code word. So 1 1 1, 1 1 0, 1 0 1, 0 1 0, 1 0 0, 0 0 1, 0 1 1 we will consider as decoded code word. So from this we can decode the message. So we can see that 1 1 1, then 1 1 0, then 1 0 1, then 0 1 0, then 1 0 0, 0 0 1, then 0 1 1. That means this path. So 1 1 1, 1 1 0, 1 0 1, then this path is considered as decoded code word. So we can find out the input. We can decode the message from this. So here it is correspond to 1 1 1. This is for thick line is 0. So 0 1 1 0. Then this is 1 0 0. So our decoded message is 1 1 0 1 0 0. So this is the decoded message. Here it is not wrote. So you should remember that the decoded message is 1 1 1 0 1 0 0. So you can check whether it is a dashed line or thick line. If it is dashed line, then the decoded message is 1. If it is thick line, then the decoded message is 0. So this is called VITERBI decoding. So this way we can decode any convolutional code. So in next class we can see what is sequential decoding.